I'm very honored to present this report. The title of my report is Coverage-Based Greybox Fuzzing with Pointer Monitoring for C Programs. I will report my presentation by 4 sections, that is background, methodology, implementation, and conclusion. As we all know, C is a widely used language in system software. However, C language implementations with their focus on performance do not ensure that developers use C's low-level memory control correctly and safely. Many methods have been proposed to detect memory errors, of which coverage-based Greybox fuzzing has proven itself as one of the most popular and practical methods. The purpose of CGF is to explore program passes as many as possible. As a given seedset, CGF uses a series of predefined mutation operators to generate new test cases by slightly modifying seeds. It implements binary instrumentation to identify which code blocks that test cases have arrived and determine the explored program passes. If a test case finds new program passes, it is added into seedset for further test case generation. Otherwise, it will be discarded. Guided by code coverage, CGF gradually generates test cases that could explore program under test in depth. Thus effectively reveals potential vulnerabilities. Point metadata and monitoring is a dynamic analyze technique to detect bugs at runtime, which commonly maintain metadata to trace pointers if unexpected condition is happening. For example, the address of the trust pointer out of bounds. It can immediately report errors with no false positives. A recent research called Smart Status has been proposed, which creates and maintains a status node to trace not only the bounds of pointers but also more information including pointer status and referent count. There are still existing challenges to CGF. Here we discuss about the motivation of the proposed method. First, most of the covered codes in a program may not contain bugs. For example, Shane had pointed out that only 3% of the code files of Mozilla Firefox is vulnerable. Therefore, treat all codes as equal and blindly extend code coverage may be less effective. Second, in C program, pointers reflect the address of memory and are directly involved in memory operation, such as allocate memory or pass parameters by referent. To some extent, pointers contribute to the low-level memory control of C and are more likely to produce memory errors. In order to achieve better vulnerability detection effectiveness, we propose to enhance CGF with pointer metadata and monitoring for C programs. This figure illustrates the overview of the proposed framework, including 2 parts: source code instrumentation and fuzzing loop. For a given source program, we firstly instrument a segment of codes to create status nodes for the pointer's objectives, which can collect and monitor pointer metadata during runtime. After that, a continuous fuzzing loop is launched. It takes a series of initial inputs as seeds to generate test cases by random mutation based on predefined mutation operators. Subsequently, those test cases are executed under the instrumented program to collect branch coverage and pointer feedback. If a test case discovers new coverage or meets preset standards, it is added into seedset for next test case generation. These steps are repeated until meeting resource limits, and meanwhile, the proposed method reports some specific errors by pointer monitoring during runtime. As the proposed method uses pointer metadata as guidance during fuzzing process, some standards are required to evaluate how valuable a test case it is, then to judge whether it should be added into seedset. So we constructed the related standards based on apparent intuitions as follows. The first one is code coverage, same as the original FL. The second one is bounds of pointers. As we know, buffer overflow is one of the most dangerous vulnerabilities, which is caused when filling the data that exceeds the capacity of the buffer. Therefore, test case with pointer address that is more close to its bound is selected. The last standard is the reference count of pointers. Intuitively, a pointer with more reference is more likely to produce bugs. This is because all the reference to parameters are points to the same memory address. Operations on one reference could lead to unexpected behaviors when other references are used unknowingly. For example, use free or double free vulnerability is caused when developers operate on the already freed pointers. We consider that pointers with more references should be focused on. Here is the example. Here we discuss the implementation. Pointer metadata and monitoring have become mature now. Chen proposed Smarters, an effective tool to detect memory errors by monitoring various pointer information. In this paper, we plan to utilize those pointer information to further guide the fuzzing process. However, there are still some challenges. To monitor pointers, Smarters instruments code segments into source program, which brings influence to coverage calculation. Most of the existing CGF methods are developed based on AFL. During program compilation, AFL inserts instrumentation into each branch of programs. Therefore, directly implementing Smarters will result in accurate code coverage, because the instrumented code segments are considered as source code. To address this issue, we plan to add an extra code comment for each line of instrumented code segments, which can help AFLs compare to identify which codes should be ignored, so that the coverage computation is the same as the source program. We plan to conduct our experiments to compare with some widely implemented fuzzers like AFLFast, memlock, and so on. The GNU binutils in version 2.26 is selected as the benchmark, which is a widely used subject. To evaluate the effectiveness of the proposed method, we employ a direct and important metric, unique vulnerability. For each cached crash, we will conduct corresponding analysis to confirm whether it triggers a vulnerability. This is because not all the crashes are related to vulnerabilities. For efficiency, set tracing points brings extra overhead. We plan to compare the number of executed test cases by each method, thus to evaluate whether the efficiency loss is tolerable. We propose to guide coverage-based Greybox Fuzzing with pointer metadata and monitoring. Specifically, static nodes of pointers are created and maintained during fuzzing process to collect extra testing feedback to affect seed selection based on the predefined standards. We have reproduced smarters and designed how to avoid the influence of smarters on coverage calculation. There are still some remaining works need to be calculated. We will evaluate the effectiveness and efficiency of the proposed method and study how to better use the extra feedback. That's all, thanks.